Welcome to the Explainer. Today, we are diving deep into probability theory. This is the incredible mathematical language we've built to find some sense of certainty in a world that is, let's face it, pretty random. Our world is just governed by chance. From something as simple as a coin toss all the way to the wild complexities of quantum mechanics, uncertainty is just a fundamental part of reality. So, how do we deal with it? How can we possibly make sense of it all? Well, we use the precision and the power of mathematics. And randomness comes in all shapes and sizes. You've got your simple, clean outcomes, right? Like rolling a die. But then you have these incredibly complex, continuous things like the price of a stock bouncing around all day. The absolute genius of probability theory is that it gives us a single, powerful framework that can handle both of these.
So here's our game plan for this explainer. We're going to start with why we even need this stuff, then build up the mathematical foundations. After that, we'll hit two of the most important theorems, see how it's all applied, and finally, we'll touch on the modern, really abstract view of the field before we wrap everything up.
Okay, so if we're going to treat probability with real mathematical seriousness, we need a solid foundation. And that foundation was laid down way back in 1933 by the Russian mathematician Andrey Kolmogorov. His system of axioms is still, to this day, the absolute bedrock of the entire field.
First things first, we have to define the entire universe of what could happen. We call this the sample space, or just omega. So, for a standard six-sided die, the sample space is just the set of numbers 1, 2, 3, 4, 5, and 6. That's it. It's the complete list of every single possible outcome. Okay, next we have to define the things we might actually want to measure the probability of. We call these events, and really they're just collections or subsets of our sample space. So for our die roll, the event rolling an even number is just the collection 2, 4, 6. The event rolling a number greater than 4, well, that's the subset 5, 6. Simple enough? And finally, this is where the magic happens. We get the probability measure, which we'll call P. Think of this as the engine of the whole system. It's a function that takes any event we can think of and assigns it a number between 0 and 1. 0 means it's totally impossible, and 1 means it's an absolute certainty.
Now, what's so incredible is that this whole powerful structure is governed by just three really elegant rules. First, probabilities can't be negative. Makes sense. Second, the probability that something from our sample space will happen is always 1. Basically, you're guaranteed to get an outcome. And third, if you have events that can't happen at the same time, the probability of one or the other happening is just the sum of their individual probabilities. And that's it. From these simple rules, the entire vast world of probability theory just unfolds.
All right, with our foundation firmly in place, now we can explore the two absolute pillars of probability theory. These are the theorems that connect all that abstract math to what we actually see and measure in the real world. We all have this gut feeling, right? If you flip a coin 1,000 times, you just expect to get somewhere around 500 heads. Well, this intuitive idea gets made mathematically solid by something called the law of large numbers. And what's amazing is that this isn't a rule we just made up, it's a theorem we can actually prove from those three simple axioms we just talked about. Okay, here's the formal way to say it. It basically says that if you take the average of a whole bunch of repeated, independent experiments, like our coin flips, that average is going to get closer and closer to the true theoretical expected value. The more times you do it, the closer your results will get to the real probability. And this visualization shows it perfectly. Look, with only 10 trials, your average might be pretty far off from the real value. But as you ramp that up to 1,000 trials or 1,000,000, that average just inevitably zooms in on that true value. The law guarantees it.
And now for the second pillar. This theorem is, and I'm not exaggerating, one of the most astonishing and important results in all of mathematics. The central limit theorem explains a pattern that we see literally everywhere. This slide really captures the almost magical idea at the heart of the theorem. It doesn't matter what random process you start with. It could be coin flips, die rolls, anything. When you add up a large number of them, what you end up with is always the same shape, the normal distribution. You know it as the bell curve. This is exactly why the bell curve shows up all over the place, from describing people's height to measurement errors in an experiment. So we have this incredibly powerful theoretical machine. Let's see how it actually gets used out in the wild. Because probability isn't just some abstract game. It is the essential toolkit for pretty much every modern scientific and engineering discipline.
In the world of data, probability is just everything. It lets statisticians and data scientists make smart inferences from just a small amount of data, build models that can predict anything from the weather to stock prices, and, crucially, to tell us how uncertain those predictions are. It is the absolute foundation of modern machine learning.
And in the physical sciences, it's just as vital. Statistical mechanics uses probability to link the tiny, chaotic behavior of atoms to the large-scale properties of matter we can actually see and measure. Engineers use it to model and filter out noise in communication systems. And maybe most profoundly of all, quantum mechanics showed us that at the most fundamental level, the universe itself isn't deterministic, it's probabilistic.
Now, to handle the really complex systems we see in science and finance, I'm talking about things like stochastic processes, we need an even more powerful framework. And this brings us to the modern view of probability, which is based on a branch of pure math called measure theory. This is where the theory gets its full power and generality. The real elegance of measure theory is that it brings everything under one roof. It unifies discrete and continuous probability. Suddenly, the difference between adding up the outcomes of a die roll and, integrating a continuous function, that difference just disappears. They're both just different types of integration based on one single powerful concept, a measure.
So this is the formal definition that mathematicians use today. That collection of events, F, is more properly called a Sigma algebra. You can think of it as just a really carefully constructed rulebook for all the events we're allowed to measure, which makes sure the whole system is mathematically consistent. Now, this abstract setup is ridiculously powerful. It lets us define probability on incredibly complex spaces, like the space of all possible functions, which you absolutely need to rigorously study things like financial models or the random path of a particle.
All right, so let's bring it all home. We've gone on quite a journey here, from just our gut feelings about chance, all the way through the rigorous foundations, to these incredibly powerful theorems and applications that really do shape our modern world. What we've seen is that probability is so much more than just counting cards or rolling dice. It is the formal language that humanity has developed to model, to analyze, and ultimately to make rational decisions in a world that is, fundamentally and often quite stubbornly, uncertain. And that really leaves us with a final thought. This mathematical framework, it doesn't just describe the world, it empowers us. By giving us the tools to actually quantify and reason about uncertainty, it allows us to ask and maybe, just maybe one day answer, entirely new kinds of questions about the universe and our place in it.